Dzień dobry. Mam nadzieję, że widać mnie i słychać. To w takim razie zaczynajmy. Łączę tylko współdzielenie ekranu z Państwem i prezentację. Niech będzie jeszcze. Powinno być widać. Okay. Jest godzina 16:16, więc myślę, że mogę zaczynać. Let's start. So this presentation will be delivered in English. And the title is Microservices and AP Gateways and Server-Side UIs. Oh my. So what I'm going to talk about is the last mile of microservices, or the connection between a microservices-based backend and the frontend. So my name is Maciej Przepióra, or shortly Mac. I'm a senior software engineer in Atlassian, where I work on Jira Cloud. I'm a molecular biologist by my education, and software developer by profession, and homebrewer by hobby. You can see some contacts here. So if you're looking for me on the social media, just use the handle Maciej Przepióra. There's some code that I develop, open source code available on GitLab. And if you want to mail me, this is my email address. And you can scan my LinkedIn with this QR code. So if you have any questions, post the presentation, post the conference, feel free to ping me. Okay. Enough about me. Let's talk about microservices. So why do people choose microservices for their backend? So why do they do that? One thing that comes to my mind is that because it's fashionable, and the programming community is fashion driven to a degree that would embrace fashion designers from New York to Paris. That's Steve Yegi, the author of the foreword to the book The Joy of Closure, and I couldn't agree with him more. When I'm talking with fellow developers, lots of people mention that, well, we're moving to microservices. And when I'm asking them, why do you do that? Well, because that's what everyone else is doing. So yeah, fashion is part of this movement to microservices. But let's talk about serious reasons for moving to microservices-based backend. So you probably have heard about a big ball of mud pattern, or rather ant pattern. What is a big ball of mud? It's the software. It's a software that has been developed the way you put a big ball of mud into your hand. Basically, you scoop some mud with your hand, and then you press it together. And that's how lots of software is being developed and has been developed so far. So basically, you just stack another feature and another feature and another feature. There is no structure in it. You just organically build it, or maybe even grow it, but there's no such thing as architecture in this software. And that's why people are thinking of ways of improving the situation for their software. And what are the problems with big ball of mud software? Well, one thing is that it's too big to be understood by one developer. And usually you could tell that, well, if you have a project or a software project that is big ball of mud, there's one or two developers in the whole company that know everything about it, and they will be able to help you with anything. But everyone who's new to the project, who's being onboarded, well, onboarding actually takes forever for them, and only few key employees know most of the stuff about the system, and then when they leave, you're screwed. So that's one problem with big ball of mud. The other thing is that everyday development is slow, because if you change something in one place, unexpected test is broken in some other place, and you don't know what's happening. You need to debug it, or investigate it, or find someone who is responsible for a particular piece of code and ask them about things. So everyday development is so painfully slow that you actually don't enjoy it anymore. The thing the other thing is that if you want to add a new feature, it takes weeks or months to deploy it on the production. And for contrast, in 2011, that was 10 years ago, Amazon was able to deploy a change into production every 11.6 seconds. So on average, almost every 12 seconds, there was a change deployed on Amazon.com. They wouldn't be able to do that with a big ball of mud pattern. That's one of the key forces that made Amazon think about microservices. Okay, then the other problem with big ball of mud, the big ball of mud pattern, is that if you have a system that is developed in that way, that is actually a huge monolithic block that is poorly segmented, it's poorly modularized, then you have a problem with scaling issues. Different parts of the system require different kinds of resources to scale for the traffic. Like an example, let's say that you have a service or a system that allows you to generate a PDF file and then allows the customer or the user of the system to sign it. So the problem here is that PDF production requires lots of RAM, lots of system memory. And signing, on the other hand, doesn't require much memory, but it requires lots of computing power, of hashing power. And if you have everything tacked together in one system or in one piece of software that runs on one piece of hardware, then it's impossible to scale on both scales, to scale the RAM and computing power. Or if you do that, you're actually overpaying, because sometimes the computing power is underutilized. Sometimes it's memory that is underutilized. So that's the problem with big ball of mud as well. So actually, let's talk a bit about scaling, because what I like to think about scaling is that there are 3 dimensions. So you have a cube that you can scale your system on, right? And the classic way of scaling is scaling by hardware. So if you have an application, you put it on multiple instances. So you replicate the application and use 3 different servers or 3 different EC2 machines in the Amazon. Doesn't really matter. You have, let's say, 3 instances. Then when the client has a request, it goes through a load balancer, and the load balancer picks an application instance that it can route the request to. So the most basic way of doing this is when you don't have state in your application, is that you just route to any application instance. The problem is that you might face issues with consistency between application instances. If you use anything like a cache or anything like that, then you will face some issues with that. But that's a really simple model, and it actually lets you scale in some way. So that's one thing: scaling by hardware, scaling by application instances. So you just replicate the instances of your application and let them serve more users. You can have a load balancer with sticky sessions, which means that for a particular customer or for a particular client, the load balancer will always route requests to the same instance of the application, and then you can keep things like some specific cache on this application instance, so that it will speed things up for this particular user. And if you have a stateful application, that's especially important, that you actually use, if you use load balancing, you actually use sticky sessions. Okay, so that's scaling by hardware. The other way of scaling, or another dimension that you scale on, is scaling by partitioning. So let's say that you have some key in your data that you partition the requests that are coming into your application. For example, by partitioning by users. So you can have application instance 1 serve users that start with letters from A to H. Then application 2 instance that serves users that have a username starting with letter J to T, and then the last one, the third one, for users with U to Z. And that's another way. We can use other keys to partition your users between instances, and that's also a way of scaling up, right? And then and the third way of scaling, which is somewhat unusual, is that you decompose your system by a functionality, and then you scale each functionality independently. And this is what I believe is what microservices are about. So basically, this is the heart of microservices. Microservices work in that way that you select or decompose your system into functions, and then the client can interact with each of those functions independently, and each of them can be scaled independently. And on this example, you can see that coming back to the PDF signing example. So if you have a client that generates PDF requests, that requests generating a PDF, that request is routed to a PDF generation service that is scaled independently of PDF signing service, because it actually uses different resources. Okay, so let's move on. That's the third axis on the cube of scaling. So let's get back to big ball of mud problems. Usually, when you work on a big ball mud of system, one of the ways to recognize that it is actually a big ball of mud is that it's impossible to test such a vast system end to end. So basically, you might have some unit tests and things like that, but since it's such a big and messy thing, you don't actually test it end to end, and you let your users test. So what is the answer for a big ball of mud anti-pattern? One of them is breaking from the monolith. So basically, not having this in one piece of software. And one thing to note here is that it's important, really important to remember that architecture really matters, even though it has very little to do with functional requirements, because software is not just a set of functional requirements that are stuck together, held by duct tape. There are also non-functional requirements, and architecture affects them a lot, like the qualities of the system, scalability, maintainability, extendability, security of the system, right? And I would dare to say that the software that just delivers or answers the requirements, functional requirements, is not enough. So, yeah, one more thing to remember when working on breaking up the monolith or breaking up the big ball of mud software is that the Conway's law. You probably have heard about it. Organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. In Atlassian, what we like to say, or we reformulate this Conway's law as what we're shipping is our organization chart. So whenever we see that what we're shipping needs to change, we're actually changing the organization chart as well. And this helps us to deliver software that has a particular architecture that we want to see in it. So enough about microservices and the reasons behind choosing microservices for the backend. Let's talk about how do clients reach the backend of the system, how to deal with external APIs, how to deal with mobile apps, how to deal with single page Ajax applications, and so on. How do we connect front end to the back end? So one way of dealing with that is that different kinds of clients consume the APIs that are exposed by services in the backend. So that will be the most simple way of having this done. And there are a couple of problems with that approach. So one problem is that you need to use fine-grained APIs, and those fine-grained APIs require clients to make multiple requests. And I've seen it happen actually when front-end developers were like, oh, well, do I really need to send 50 requests before I can display a particular view? That doesn't make sense to me. Why can't I just send one request and get all the data back? So that's one problem. The other problem is that clients like JavaScript web applications, iOS applications, Android applications, or third-party applications, they know too much about the internals of the system. So it's really difficult to change architecture and APIs. And what is the most important here is that if you make a change in the backend service, you need to roll it out to clients as well. And this needs to be synchronous. So you cannot just change the PDF generation service and leave it as it is, right? You need to change all the clients, and the same thing with other services. So if you, let's say, if you have a backend that is composed of 20 microservices, which is not unusual, and you have three different kinds of clients that are using it. If you would use this deployment model, that would mean that you have to actually care for 60 combinations of rollout. That's just unmanageable. So that's one thing. Then, if you have some back services in the backend, they might use inter-process communication mechanisms or inter-service communication mechanisms that are unwieldy outside the firewall. Like, for example, what we usually expose is REST, but some services might use Google RPC, and it's not a good idea probably to expose your gRPC service outside of the firewall. So that's another problem. And the third problem, if you're exposing your APIs or your system to third-party applications when you're building a platform or something like that, your clients, third-party apps, they expect your API that is stable to be stable. It needs to be stable so that they don't get surprised with the changes that you've made to the API, right? Excuse me. So these are the problems with this naive approach of having backend expose all services to the user. So that's why the API gateway pattern, the first front-end to backend pattern, emerged. So this pattern allows you to separate or shield backend services from the front end, and API gateway is the actual place where your clients send requests to, and it takes care of forwarding them to backend services. It might take care of things like translating the requests from clients to a format that is understandable by your backend services. But the basic idea is you want to shield backend services from your clients, and that's how you can approach this problem. So you have an API gateway in the middle, and it takes off some kind of routing the requests. So that's one thing, request routing. An API gateway also allows composing the APIs, so it actually allows you to show one API that is actually composed of many different APIs of the backend services. I've mentioned protocol translation already. It can take care of things like switching from HTTPS to HTTP and so on and so on. And you can have actually different implementations. You can have one size fits all API gateway, or you can have an API exposed for particular client types. What is more, API gateway can take care of edge functions. What are edge functions? These are things like authentication, authorization of the requests, rate limiting, caching, collecting metrics, login requests that are coming to the backend, and so on and so forth. So you can actually bake those edge functions into your API gateway, or you can have them separately. So that's a dilemma actually. How to deal with that? Should they be separated or should they be together? So if you separate them, then one pro for that is that you separate concerns. But the con here is that you add a network hub, so there is more latency and there's additional complexity. So how it would look if we had edge services baked into API gateway. Well, each module either routes requests to backend services or composes response from multiple requests to the backend, and you can have the common layer that's basically the edge services, and you can deploy it on one as one piece of software, or one service, the API gateway service. But you can also have backends from frontends. That's a variation of API gateway pattern that basically looks like this. So there's a separate gateway for each kind of client. What is more, they are separately deployed and separately scaled as services, but they have a common layer, the edge functionality that is probably being developed by the same team, by one team that takes care of it. And when you take this approach, you need to remember that since you have edge functionality embedded into the API gateway, and this edge functionality is being developed by a single team, you probably want all the API gateways to be developed in the same technology, like to use JVM, for example. If you're using JVM, you can use different languages on the JVM, but you still would need to use JVM if you were using JVM technology. Or if you're using .NET, you could develop the edge functionality in C# and use F# for API gateway in one instance, for example, for SPA, and some other .NET language for a third-part API gateway. But still, you need to have the common technology behind that. Okay, so excuse me, how to implement these patterns, the API gateway patterns. One thing is that you need to think about is that whether are you going to use a product or roll your own. And many of the cloud providers offer their API gateways, and well, you need to look in the particular functions that are provided by this provider that you use, if it fits your requirements or not. So you can use off-the-shelf service. Other way is one example is AWS API gateway. So it also provides edge functionality, but last time I checked, it doesn't support API composition. It requires your system to run on AWS, which might not be something that you want to do. It only supports HTTPS and is heavily puts heavy emphasis on using JSON. So that's, well, you need to look into that, read the documentation, and figure out how to deal. Is this the answer to your issues? Or you can use product. There are a couple of different API gateway products. I've heard about Kong. and it is you can develop plugins for it in Lua, the scripting language. The thing with Kong is that Community Edition, the one that comes for free, it's very limited in its functionality. So that's one product. The other one is Traffic. Traffic is a paid Traffic Enterprise is a paid gateway API gateway, or you can use Tick. That's another product, or you can roll your own, develop your own API gateway. And to do that, you could probably, for example, if you're on using Java and building in Java, you could use Spring Boot Gateway. So that's one. But API Gateway is not everything. You can actually implement an API gateway with graphs. So what I'm thinking about here is inverting the control. Instead of trying to straitjacket clients into the APIs that you provide for them, you can let them choose what data is returned. And that's the basic idea behind GraphQL. There are different implementations of GraphQL standard. The reference one is Apollo, that is built for Node.js. And it's built by Facebook, the company that developed GraphQL. Or actually, it's Meta now, I'm sorry. But GraphQL originated at Facebook. In 2018, it was started to be used by Facebook. The community picked it up really quickly. So one implementation is Node.js. For Node.js, it's Apollo. There's also a Spring Boot implementation that allows you to build GraphQL gateway. So yeah, depending on your technology, you should be able to develop your GraphQL gateway on your own. So that's Apollo. And the last thing that I want to talk about today is implementing a gateway with server-side UIs. So you can try to invert the control even further. So with server-side UIs, you can actually embed the client on the server side on your infrastructure, and use the client, the browser, for example, to render views only, and nothing more. Basically, you run the UI on the server side, and the browser is just rendering that UI to the end user. And let's look at layers in that case. So let's say that you have a JavaScript client, JavaScript application that uses some kind of transport, like REST calls. You have API gateway that connects it to the backend services, and that's it. With client-side UI, what you need to take care of is developing JavaScript client, developing the communication layer, like data transfer objects and so on and so forth, and and developing your API gateway for the front end, right? Because API gateway is actually, while it's being deployed on your server side, or something that you would classically call the server side, it's actually part of your front end because it provides the API for your front end to use. So that's one thing. But when you use server-side UI frameworks, you can have the communication and JavaScript client automated, provided by the server-side UI framework. And you just develop an application that runs on the server, that keeps the state on the server and connects to your backend services. And one of the frameworks that implement this model for Java, it's Vaadin. You can check it out at vaadin.com. If you ever developed a windowing application, like let's say with Swing or with abstract window toolkit or SWT, it feels very familiar, because what you're doing, you're actually developing your UI as a tree of components that have click listeners and so on and so forth. And then since it runs on the server side and uses the browser only to render the view to the user, you're not you don't need to look into the communication. You don't need to develop the communication layer. You don't need to develop the client-side application, basically. And a final thought. So if you think that good architecture is expensive, you should try bad architecture. That's something good to remember, because one thing that you can face when trying to break from the monolith and stop doing the big ball of mud is that we don't have money, time, or anything like that. Well, it usually pays off to do the right thing. Okay, that would be pretty much it of what I had for today. I just wanted to say that Atlassian is hiring in Poland. We have an office in Gdańsk, but we're actually hiring for remote positions, and pretty much any position at Atlassian currently is remote. So if you want to join the company that is behind Jira, behind Confluence, behind Trello, feel free to apply. If you have any questions, again, ping me on LinkedIn and I will be glad to answer those. Yeah, and the QR code on the left is a jobs listing for Poland. So feel free to hop in there and figure out if there's something that is interesting for you. Well, let's see if we have any questions. So I'm going to stop sharing the screen and see if there is anything in QA. Apparently not. Well, that's it. Thank you very much.